right now. So I've got- All right. So first of all, thank you for joining our lecture again. We had an office hour yesterday, 2 o'clock, and I have like two or three students came in and asked me questions, and it's more about some of the details for the last homework, and I will go over them real quick. And in addition to that, the office hour video, basically I had with Kyle, I believe, that is uploaded yesterday to the YouTube. Subsequently, with the other student, I didn't get to record it because they're so short. But the notes on the self weight, especially how to calculate that, the details are has been uploaded to the file tab on Canvas. You can find it under like office hour name. So that's that for the office hour. And let me go ahead and start talking about some of the problem you might have seen so far on the homeworks. Okay. So give me 1 second. I'm still seeing a lot of people coming in right now. Okay. Nevertheless, let me try to do this. Share screen and iPad. Okay, so let me do here. All right. Okay. All right. So I hope you can see it. And this is the some of the homework related questions. All right. Now, first thing is about this minimum reinforcement. Minimum reinforcement. Now, we have talked about analysis on the singular reinforced and doubly reinforced section, right? So that is the final moment capacity and strength reduction factor for the section. Quickly recall, you always are given the reinforcement in the design, okay? So that means like you always know what kind of reinforcement you have for the section, and you just find out the moment capacity using the Whitney stress block approach, Okay, now in hindsight, people haven't asked about these questions. How much reinforcement is needed? Okay, so in terms of reinforcement, there's a story behind it. All right, now back in the 50s, where people just preparing reinforcement structures, and there's an airplane hangar where they have a sort of like a cantilever beam. Okay, sort of like a cantilever beam. So in the cantilever beam setting, now, if you don't have a whole lot of reinforcement, say you just have minimum or no reinforcement at all, and by calculation, we calculate the cracking moment MCR, and if we say that after we do this calculation, the applying moment MU, should I write this way, is smaller than the MCR, of course, there's no strength reduction factor here because there's no reinforcement, right? We naturally assume the beam is okay. The beam is okay. So we went ahead with that design back then, but eventually the beam cracked. The beam cracked. And knowing that it is a cantilever beam and only suffer self weight, so the whole beam cracked right here on the end on the top, right? That's the major tensile crack. That's the major tensile crack. All right. So this accidental failure really make a big notes to the designers, because back then people think, well, as long as my design is adequate, why accident like this happen? But there is a statistic variation in terms of materials properties, aging, and all that to do with concrete structure. So people decided based on this instance that we need to provide a minimum reinforcement, Okay. All right. So that's the concept of minimum reinforcement. Let me change this to be a little bit smaller. Okay. So that means even if your cracking moment already satisfy your apply moment capacity, you still need a reinforcement in the section. All right. You still need a reinforcement in the section. So ACI in the section 9.6.1.2, okay, 9.6.1.2 gives you the equation for the minimum reinforcement. Okay. So here are the two equations. So I just copied it from ACI. So I want to read it out loud for you so we can go through some details. So AS min shall be the larger of A and B. Okay, so basically AS min, that's the minimum reinforcement, should be larger of two things, right? A, that is 3 square root of F prime C divided by Fy B W D. Okay, and B, 200 divided by Fy B W D. Okay. Now, in case you find other equations from A side code, that's not it, all right? This is the only equation for our flexure strength design. Okay. Don't use the wrong equation. These are the correct equations. Okay. Now, going explain a little bit. Of course, this square root f prime c here. Now, only thing you need to be careful is that this unit here for f prime c is psi. Okay. Unit here is psi. All right. So don't use KSI, okay? Because the square root have unit in it. Square root have unit in it. The second thing is, let's talk about this BW, okay? What is this BW, right? So let's take a look at the section. So it wouldn't be hard because if I have a rectangular section like so, and this is my only width of the section. So naturally, for rectangular section, B equal to BW. Naturally, right? B equal to BW naturally. But how about IB? How about IB? Right? Under this circumstances, the BW, is it like the flange width, BF, or the web width, BW? Of course, right? I already leaked out the secret, right? It is BW, right? It is the narrowest width of the section that count as BW in the equation, right? So on and so forth. How about a T-beam? How about a T-beam? So again, this is BW for the web, and this is BF for the flanges. So of course, we're talking about BW. Okay, is the narrowest width. Okay, narrowest width. All right, so that has to be careful. Now D, where's the depth of the section? Depth of section. Now you make it confused again. Say, Bob, you talk about in the section that we always shown there's a beam, and you draw the height. We understood, and you have the width. For this case, we understood. And now, how about reinforcement, right? So I have reinforcement at the bottom here, and if it's group of bars like 2 rows, now I end up with 2 things, right? One is that for the center of the group, I have this so-called ds, okay, ds, and also for the last row of the bars, I also have dt. So all of a sudden, you also have this as a D equation here. So which one is which, right? So for this purpose, D equal to DS. Okay, always, almost, always, right? D equal to DS. That is the effective depth. Okay, so let me just label here. So this is so-called the effective, so-called effective depth. Okay, effective depth. Now, what does dt do here? dt, remember, is only needed when we need to find the epsilon t and find out the stress reduction factor phi, remember? Okay, so there are 2 separate concepts, 2 separate concepts. Okay, so this is about a minimum reinforcement, Okay, now what are we gonna do about this minimum reinforcement? Let me just put this down a little bit, okay? That is once you have calculated the section capacities, right? For example, if I give you this is AS, okay, you simply have to make sure AS, or we call it AS provide POV, or you can just say AS, okay, AS has to be bigger or equal than AS min. And AS min equal to larger of 3 square root f prime c bfy bwd and 200 of fy bwd. Okay. Now I forgot one thing, the fy is the yield strength, of course, yield strength of the steel. And for a grade 60, that is also what? Fy equal to 60,000 psi. Okay. Here we also use the unit psi for this minimum reinforcement equation. All right. So now in your homework, at the end of the capacity check, all you have to do is just to make sure that this equation holds. Okay, this equation hold. All right. Now we'll talk more about this when we get down to the design section, but I still want you to know this concept. Okay, and you don't need a whole lot in the homework. So that is the first clarification on the minimum reinforcement. Minimum reinforcement. Second, self-weight. Second, self-weight. Now I'm showing here that's the typical beam section, right? So I actually took this, for example, from a segment of a simply supported beam, for example, okay? segment of simply supported beam. And imagine that I only have self weight, right? I only have self weight of the beam. Okay. And we also talk about this. We say this is omega dead. And you will find that typically they're in a unit of pounds per linear foot. Pound per linear foot. Okay. Now, if you really think about it, what is the soft weight, right? Soft weight essentially is just the density rho multiplied by the volume, right? Multiplied by the volume. But since it is per foot, what we do is we need to specify a volume that has a width of B, of course, the width of the section, height of the section H, and a thickness that is just 1 foot. Thickness is just 1 foot. All right. So in this way, the soft weight omega per foot is rho BH 1 foot. Okay. Now, what is the density for concrete? And we talk about this. Okay. We talk about this. This is rho equal to 150 pounds per cubic foot. And that is for normal weight of concrete. That is for the normal weight of concrete. All right. Okay, so this is how we calculate soft weight. All right, so with these two get out of here, you should be able to fully complete your homework number 2. All right, now I have gotten your homework number 1. I'm halfway grading through it, and it should be released. The grades should be released either today or tomorrow, and take a look out for that. Okay, and now for the homework number 2, the due date is tomorrow, Thursday. Okay, so try to finish it up tonight. If have questions, just email me. I'm pretty good at answering email. Okay, so if you have any question, we can also schedule a Zoom chat and can go over some of the problem for you. All right. Okay, I'm just gonna pause for a second. Any question about homework number 2, folks?
When's it due?
It's always due on Thursday, every Thursday, and you go on the Canvas.
What
There's
time on Thursday?
a midnight.
Okay, thank
That's
you.
what that's what I'm saying. So every time you go onto the Canvas, there's let me show you right now. Okay, I have a question from Chess. Do we have to take into account the reinforcement software? No, that's a good question. But the reinforcement is normally so small amount, you don't have to worry about it. Okay, do we need to subtract the area of steel bars from the, again, a good question, but it's a very small amount of area, so we normally just ignore the steel in the section. Okay,
If we did do that and then we already turned it in.
that's okay. I won't deduct the points because your
Okay.
number will be very close to just the concrete. That's actually a good point. It's just going to be a good check. Okay. All right. Okay, so let me stop sharing my iPad for a moment. And I want to switch back to the Canvas. I want to show you how to navigate Canvas. A lot of students ask me now questions about the Canvases, okay? A lot of information here already. So if you go to your Canvas tab, you should see the screen like this. And in my case, I click on a course. My favorite course is this Arch, that's Civil Architecture 3220. I combined 2 sections into one, RCDesign Spring 2021. This is the tab you want to hit. Once you hit it, it goes into the course, and the first thing jumps out is the syllabus, yada, 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 yada. You have seen that before. And on the left-hand side, there are tabs here, right? So if you want to figure out what are the assignments and all that, you go to assignment here. You can see that, well, I already list them, okay, categorize them into assignment. This is number 1, this is number 2, and the due date is right down here, okay? Due date is right down here, the time, everything, okay? And if you submit late, I also receive a late submission, all right? Now, there are also quizzes, okay? And the quiz deadline is also listed here. And I normally leave the quiz during the lecture. I won't post them. So it's kind of like a check if you attend the lecture or not, all right? So be sure you watch my lectures and get this quiz content, okay? If you have a question on the quiz content, email me. Right here is an exam tab. We don't have any exam set yet. Like I said, I'm still confirming for this first exam. Most likely we're gonna do this online for the first exam, but just wait for me to confirm that. But if the exam is gonna show up here, you won't be able to see exam here. They will be sent to you in a very private link where you can yourself only have the access. And everybody might have a different version of exam, okay? I just want to caution you, okay? So that's how you navigate on assignment folder, okay? Now, we don't usually use discussion a lot. Like I said, email me and I can set up individual meeting with you. All right. Now, for your purpose, okay. Now, this here file is very critical. Okay. If you click on files, you see all the files we have talked about so far have been uploaded here. homework number 1, homework number 2, 3, and 4, etc. in the future. And lectures 0, meaning those are PowerPoint lecture, chapter 1 to 3. And also there's some talk, some illustrations on the PowerPoint. That is lecture 0. And lecture 1, I have the date behind it, lecture 2, 3. You can find the YouTube, okay? YouTube link right here. If you click on this YouTube link Word file, that's the link that will go to my YouTube channel where you can watch all the lectures by date. They're listed by date, okay? Now close this one. And there's also Zoom link. That's the link we're using right now. I should have figured it out by now because we're talking right now, but in case you forgot, this is where you can find it, and there's a phone access and everything, so you should be good. Okay, so that's all you need to find out. And also there's office hour notes as here, so you can take a look at office hour, and then you can take a look at what we talk about during office hour. Okay, now let me stop sharing this, coming back to my iPad, and also got an interesting question. Can we go over how to find the strain and steel number 3 and number 2 and number 3 of the homework? I'm sorry, Henry, those are talked about already from previous lecture. You can try to do it yourself, follow the lecture notes. If you have a trouble, email me, we can set up individual meetings, okay? All right, okay, so that's that. Now let's come back to the main lecture. So sharing screen again. See if I can do this. Work. Okay, pretty good. All right, so we have cleared the two confusing point. Okay, one is minimum reinforcement. The other is how to calculate self-weight. Now let's enter lecture 4. Okay, lecture 4. So lecture 4, and just to fresh your mind and remind where we're at, we're talking about doubly reinforced section. We're talking about doubly reinforced section. Okay, doubly reinforced section. All right. So what are the doubly reinforced section? What are the doubly reinforced section? First of all, okay, the most important thing is we add compressive reinforcement. Compressive reinforcement. That is the most critical element in the doubly reinforced section. And we have talked about this. The main reason to add compressive reinforcement is not to increase the capacity of the beam, is not to increase the capacity of the beam. On the matter of fact, the reason why we supply compressive reinforcement is to ensure we have increased ductility. Ensure we have increased ductility. That is, if I use blue line, and this is without AS prime, and I use the red line to show that this is with AS prime. Okay, now you see that the strain in the steel, epsilon s here has been increased significantly. Okay, so the purpose of giving or providing compressive reinforcement is to add ductility. Okay, ductility. Such a strange word. What do you mean by ductility? Ductile, right? Ductility means that I increase the strain in the steel. So if I increase the strain of steel, okay, think about another consequence. What really happening is that possibly I also increase my phi, strength reduction factor. Okay, now in case you forgot why we will increase phi, so think about phi as equation, remember? So it's all about epsilon t. Okay, all about epsilon t. Now be careful, okay, this is epsilon s. Epsilon t is the last layer. In this case, they're the same because a single layer. Multiple layer, a little bit different, but epsilon t dictates what the phi looks like. And remember, for phi, if epsilon t is 0.02 and 0.005, they have different numbers. Below 0.02, you have a 0.65. Beyond 0.05, you have 0.9. Okay, and in between there's a linear interpolation. Okay, so if I have my points right here, for example, here, okay, now before adding compressive reinforcement, maybe it's here, okay, this is before. Now add compressive reinforcement, I may went all the way up here, maybe, and then I increase my phi. Okay, the point of increasing phi is that it gives you a little bit added capacity. But like I said, the main issue, the main purpose is to increase the strain in the steel, to let the steel properly yield, to give you that sufficient reinforcement. Okay, now I said this 3 times already, and make sure you understand this and remember this, because this will show up in exam number 1. Okay, this will show up in exam number 1. All right. Okay, so quickly when review, right, what we talked about last time. So we examined the stress distribution or strain distribution inside this doubly reinforced section. Okay, inside the doubly reinforced section, and we said, the strain is going to look similar than the singly reinforced section, and this is epsilon Cu, and mind you that is 0.003, and I have a steel right here, and that is epsilon S, and I have the actual compressive zone C, and now I have a little bit additional things, and that is epsilon S prime. Okay, and of course the internal stress distribution, I have a Whitney stress block again. This is 0.85 F prime C, nothing different. And I have an actual compressive zone A, and I have a stress in the compressive reinforcement steel F prime S.
Hey, Professor,
Yes, sir.
would the ES or the epsilon S and epsilon S prime, would they technically be equal because that's the
Nope.
modulus for
Nope.
steel? Or
No, they're not at all, right? The reason is that, good question, by the way, the effective compressive zone C is not half of the section. They're not. Okay, it's not symmetric, isn't it? Okay, why is that? Look at the internal stress distribution, right? On the top, in the compressive side, I have concrete, but in the bottom tension side, I have no concrete because concrete has cracked already. I only have the stress from the steel. All right.
okay,
Okay, so it's definitely not. Okay, almost for sure it's not equal. Okay, and the reason is that section is not symmetric because the materials property is not symmetric. All right.
I got you. I got you.
Yeah, okay, good deal. Okay, now for the internal forces, right? Internal forces, I have concrete here, we call it CC. Okay, I also have compression from the steel CS, and knowing that the distance for the concrete force is half A, and CS, the distance right here is ds prime, Okay, and now the tensions right here. And again, if you really want to say that there's a lever arm, the JD, of course, here, that is D minus half A still. Did not change a bit, All right, different from the singly reinforced section, I want to write down the equation. For strain, okay, what's happening is that epsilon S prime, that is the compressive strain, minus, divided by C minus ds prime, okay, and equal to epsilon Cu and divided by C. So epsilon S prime equal to C minus ds prime over C and multiplied by epsilon Cu. Okay, so that is the strain in the compressive reinforcement. All right, now talk about internal forces. Right? Now, in addition to the concrete, where we know concrete CC equal to 0.85 F prime C and beta 1 C. Now, you may see this first time, but beta 1 C equal to A and multiply B width. Okay, and now that is for concrete. For steel, CS equal to AS prime and multiply F as prime minus the 0.85 F prime C. Remember you talk about subtract the reinforcement. This is the only place, okay, let me say this again. This is the only place you subtract the concrete where you do it here, okay? Subtract the concrete. Now Fs prime, where is the compressive stress in the steel, now equal to, this is by the way stress, okay, equal to ES, okay, that's the Young's mass of the steel, which is 29,000 KSI, you should remember by now, multiplied by epsilon S prime, that is the compressive strain you calculate, and you have to make sure, okay, I want to emphasize this is smaller than the yield strength, all right? So you say, Bob, wait a minute. You say the tensile reinforcement has the yield, right? And the compressive reinforcement didn't get to yield? Yes, exactly. Because we are not allowed, so compressive reinforcement, okay, is not allowed to be yielding. Okay, it's not allowed to yield. Okay, it's not allowed to yield. All right. Now you say in the extreme case, what if the stress is indeed yielded? If yielded, which is bad. If yielded, we have to use Fs prime equal to Fy. That's it. Okay, Fs prime equal to Fy. So it's capped. It's capped. But honestly, we don't prefer the compressive reinforcement to yield. Okay, if your compressive reinforcement yielded, either you provide too less of reinforcement or your section is inadequate. Section is too small. Okay, now we talk about that case when we cross the bridge. Okay, but for now that's all we want to say. And now for the tension T, okay, this is from the ASFY business, right? ASFY business from the tension side. Now change that equation to equal to CC plus CS. Okay, from both compression, or and we have covered this, ASFY now equal to two components 0.85 F prime C and B and beta 1C or A plus AS prime multiply Fs prime minus 0.85 F prime C. Okay, all righty. So that is our new equilibrium. New equilibrium, okay, new equilibrium. Okay, why I said new? Because this is for doubly reinforced section, doubly reinforced. Okay, all right, okay, so this is for doubly reinforced section. Now up here, I mean up to this point, we have covered all the concept mechanism, but to really calculate things a little bit different. Things a little bit different. Why? Because, okay, since it is a nonlinear function, okay, nonlinear function, which means this governing equation of equilibrium is nonlinear. Why is that? Why I call it nonlinear? Think about it. I don't know the F prime C unless I know C, which is the actual compressive zone. Okay, and I have a C here as well. So essentially, I will end up with a second order equation C and try to calculate that because my strain in the steel also depends on the actual compressive zone. Okay, so it's very challenging to solve it on the side by hand. Okay, well, use calculator Excel sheet you can, but that's complicated. So we have to come up with a simplified procedure to do that. Okay, so this is the real design or analysis procedure for it. Okay, so first step, what we do, we assume, okay, we assume the tension steel tensile reinforcement. That means AS, okay, AS yielded is yielding. Okay, meaning epsilon S bigger or equal than epsilon Y. All right, so that's first step. Now the second step, we select, okay, this is very important, select a actual compressive zone C. All right, so what to select? We select the C that belongs to the range of D over 4 and D over 3. You say why, Bob? Well, that's an experience. Okay, we normally select the value between quarter of the depth to the third of the depth to start with. Okay, once you arbitrarily, and this is arbitrary select, there's no rationale. Okay, this is just by experience. Okay, I select an actual compressive zone C, and I can compute my strain and the compressive reinforcement using the equation C minus ds prime divided by C and multiply epsilon Cu. Now, once I have my compressive strain of the steel, I can compute my Fs prime, that is Es epsilon S prime, to get my compressive stress of the steel. With that, the next step is to do
Could you scroll up real quick to like step 2
here.
and 3? Thank you. Thank you.
Sure, not a problem. So CS is the compression of the steel, and 6 that CC is the compression of the concrete. All right, CC is the compression of the concrete. So once I have the compression side, I will say tension side T equal to ASFY. That is the tension. All right, and now I will just have to say, look, what happens? What happens is that I select a compressive zone size C. Okay, I come up with the tension T. Okay, if now T, the tension is greater than the compression. Okay, now I have to what? Increase C and return to step number 3. Okay, meaning I underestimate my actual compression on C. I have to redesign it. So I increase C, run through again. And if my T came up short, smaller than CC plus CS, what I do, of course, I reduce the C and return step number 3, do it again. So the whole purpose, right? The whole purpose of doing this iteration, right? So thinking in your head essentially is that I'm doing this iteration here. Okay, doing this iteration here. Okay, so change C. Okay, and why am I doing this iteration? Just to ensure that T approximately equal to CC plus CS. Tension equal to compression, approximately. All right. You say, Bob, so many words. What do you mean by approximately? When I say approximately, is that error must be less than 5%. 5%. Preferable less than 3%, but normally less than 5%. Okay, very critical. So this
How
is
much
like,
do you increase T by?
well, that's up to you, sir. Whatever you want to do it. Right? We'll go through an example. You can take a look, have a feeling for it, but there's no rules. You just do it by yourself. Okay. All right. Is it clear?
Okay. Yeah,
All
yeah, yeah.
right. No problem. Yeah. So here, this is a critical, okay, critical decision point, whether you satisfy this equilibrium or not. If this is satisfied, that is, if you satisfy the step 9, strain in the tension side again, check, right? This has to be bigger than the yield strain, right? Bigger than the yield strain. Okay. And then if this is the case, right, this has to be satisfied. Then you find the phi stress reduction factor by what? How do you find it? You use epsilon T, okay? And that is dt minus C divided by C multiply epsilon Cu. Okay. Multiply epsilon Cu. All right. And then at the end, once you have phi, and you can easily compute phi and compute the moment capacity Mn. Now, since it's doubly reinforced section, right? So Mn is a little bit different as well. Mn no longer equal to T d minus half A, right? It becomes Cc, where is the compression force, and this is d minus half A plus Cs d minus ds prime. Okay, so sorry, this is ds. Okay, ds minus half A and ds minus ds prime. So folks, if I sometimes say d, that is ds all the time. Okay, ds all the time from old world, by the way. All right, so talk about this equation. Why this changes? Now think about it for internal forces, right? I end up with concrete compression cc and steel compression CS. Usually CS is higher than CC, okay? Now I also have a tension force T here. Now the lever arm distance, right? What I'm trying to do is I'm summing the moment with respect to tension. Okay, so you can write down here, this is basically summing moment with respect to tension. Okay, so why, Bob? Because I reduce one additional term, all right? So the distance between CS and T, right? Think about it. This is D, and this is top fiber, okay? And this is ds prime. So the distance between CS and T is ds minus ds prime, okay? And now the distance between the concrete compression to the top edge is half A. So the distance between CC and the T is ds minus half A. Okay, hence I have this equation. All right, so I'm summing moment with respect to the tension side of it. Okay, alrighty, so that is the correct procedure. That is the correct procedure. Okay, for double reinforced section. Now with this, let's take a look at an example. Okay, take a look at an example. Okay, example 1. So for a doubly reinforced section, below, shown below, and I have known the concrete capacity is 4,000 psi, roller ready mix, and we have a grade 60, okay, steel, and I want to find out, and by the way, for steel, if you don't remember, and you should and you will from the first exam coming, and it's got to be 29,000 KSI, Young's modulus for the steel, okay? I need to find out my MN and my phi, all right? So what does the section look like? The section look like this, the typical rectangular section, nice and easy, okay? And having a top compressor reinforcement, three, you guessed it, number 9 bars, my favorite, number 9 bars, okay? And a concrete cover, or you can call it DS prime, that is equal to 2.5 inch, 2.5 inch. All right. Now the height of the section is h equal to 20 inches, and the width of it, sorry, it's really hard to draw here. The width of it is b equal to a 12 inch. On the bottom side where the tension's at, I have one, two, three, four, total 6 number 9 bars, okay? Total of 6 number 9 bars. All right, and now as usual, my concrete cover here, and you will see this number from all our examples that for a single row, okay, single layer, the concrete cover is typically 2.5 inch. Okay, for two group of bars, I mean, 2-layer bar usually is 3.5 inch, but nevertheless, this continue is not important here, okay? So that is the configuration of the reinforcement. So let's solve it. Let's solve it. So step one, right? Step one, assume the tensile reinforcement yielded. So the stress in the tension side of it equal to Fy. And step two, select concrete compressive zone size C between D over 4 and D over 3. And again, if I forgot to put S here, put it yourself for me, please. That is the effective depth, okay? So from this, I know that the depth is 20 inches. 20 divided by 4, right? That's about like what? Sorry, ds, right? Sorry, it's not height. ds equal to 20. All right, now I'm gonna make some approximations, right? I'm gonna make some approximations. I know that I have 2 rows, okay? And I have a distance between the first row and the second row. But to make it easy on us, right? I'm just gonna use a known depth, right? I'm just gonna make a known depth to make it simplify for us. That I would say ds is given 16.8 inches. In reality, you have to calculate yourself, and we have demonstrated how to do that before, okay? So, hated this. So ds is 16.8 inch, okay? It's given here, but you might have to do it yourself for homework and for the exam, okay? Now, ds over 4, that is 4.2 inches. ds over 3, that is 5.6 inches. So between, right, I need to pick a number between. So I say, you know what, I'm going to try a wholesome number of C equal to 5 inch. Why? Well, it's between the range, and I like this number. And besides, I know the answer, right? I'm just gonna pick some number close, right? So I'm just gonna try C equal to 5 inch. So next step, I want to compute the compressive strain epsilon s. So epsilon s prime, and that is equal to C minus ds prime over C, and multiply epsilon cu. Okay, C in this case, now I pick this number, right? So 5 minus 2.5, okay, and divided by 2.5 and multiplied by 0.003. So I got this number to be roughly equal to epsilon s prime equal to 0.0015. Okay, and now I can move forward to compute my stress in the compression side of it. Fs prime equal to Es multiply epsilon s prime, Es equal to 29,000 KSI, okay? KSI, pretty huge number,
Hey,
okay?
Professor,
Yes, sir?
for step 3, shouldn't it be 5 minus 2.5 over 5?
Oh, sorry, you're right. Yes, thank you so much for the correction. Is that good?
Yep.
Alrighty, thanks a lot, okay? So now Fs prime equal to 29,000 KSI, large number, multiply 0.0015, and I have this number to be 43.5 KSI. Now I'm very happy about this number. Why is that? Because this is 43.5 ksi, and that is smaller than 60 ksi of yield. Okay, so I decided and feel pretty good about it. Okay. Now no yielding and compressive reinforcement. Pretty happy about it. Okay. Now with that, I can let me just move a little bit towards the left. Okay, because I have a lot of things underneath it. Okay. So sorry about this misalignment, but CS now the compressive reinforcement gave me the compression force of AS prime. Okay. Don't forget Fs prime minus 0.85 F prime C. Okay. Now AS prime, what is area, right? What is the area? So I'll count the bars. I have number 3 and number 9. I have 3 number 9 bars. Per each number 9 is 1 inch squared, so 3 inch squared. Lazy bar. Hey, I know that. Very simple, right? Now FS prime is 43.5 KSI, which is computed minus 0.85 multiplied by 4 KSI of the concrete. Okay. So you got this number to be 120 kips, just the compression from the steel. Imagine that. Okay. And now for the concrete, so CC equal to a 0.85 F prime C, now B and beta 1 C. Okay. And 0.85 stays there, 4 KSI of concrete, B is 12 inch, and 0.85, this is what? This is beta 1. Okay. This is beta 1. And C, what is C? C is 5 inch. Why? We picked that number. Remember? We just guessed it. And now this is what? This is 173 kips for the concrete. For the concrete. Okay. All right. So now step number 7, T, which is tension side equal to ASFY. And that is what? 6 number 9 bars. Okay. And yielded 60 KSI. So have a 360 kips of total tension force, right? And now let's check if the balance is holding, right? So CS plus CC, that equal to 293 kips, okay? And turns out that is smaller than T equal to 360 kips, much smaller, okay? No good. So why is much smaller? This is less, right? This is much less than 5%, more than that, okay? More than 5% less. So what we're gonna do, all right? Now, look, compression is smaller than tension. So think about in your head, I have the strain distribution like this. So essentially saying that, the compression side is smaller than the tension side. So when that happens, what you do, you increase the compression, right? To balance it out. So in this case, I would say now increase, increase compressor zone C. Okay, increase compressor zone C and return to step 3. Remember, return step 3. Okay. All right. Now we're supposed to return to step 3, right? And go through the steps again, right? Rewrite the whole thing again. Now that's really tiresome. I'm tired already here, right? Used up all of my energy from morning coffee, right? I'm done. So I don't want to do this. I'm gonna cheat, right? So how am I gonna cheat? I'm gonna make a table. All right. I say let's use a table. Okay. Think like a computer, right? Think like a computer. So let's list on the left hand side. That's my compressive zone C. Okay. That's my compressive zone C. Okay. And next column, okay, I'm just going to compute epsilon s prime. And the equation is C minus ds prime over C and multiply epsilon Cu. All right. And then next step is to do Fs prime equal to Es epsilon s prime. Okay. And then Cs then equal to As prime. Okay. As prime multiplied by Fs prime minus 0.85 F prime C. Okay, sorry, let me extend it line a little bit. All right, and next line is C equal to CC equal to 0.85. Okay, F prime C B beta 1 C. Okay, next one is tension T equal to AS Fy. All right, and then next one is CC plus CS. All right, so I made this table. Okay, and in the exam, I expect you to finish at least one process like this, okay, like I just did. And now you can use the table. You can use the table. All right. So what do I put on the right-hand side of the table? What do I put on the right-hand side of the table? Okay. So I'm going to use first number, which what we did is 5 inches, but we already did 5. So let me just use 5.5 for next. So why? Well, we decided to increase C, right? And answer the question, Louis, well, I'm just going to use 0.5 increment for this point, for this problem. Okay. Now, if I increase to 5.5, all right, and I'm just going to jump ahead. Okay. You get some number like here, you get some numbers on the epsilon s prime, get some number fs prime. I'm just going to save that. You can fill it up yourself. And the compression force at 5.5 of actual compressive zone is 132 kips for the steel and 191 kips for the concrete. Okay, and this end up to be tension side is 360, and this ends up to be 323 kips. Now this still not good enough. Matter of fact, this is 10% lower. Okay, 10% lower. So what I do is still lower, right? So I'm going to keep increasing my compressive zone size C by 6 inch. And again, you can fill up yourself. And then here I got 142 kips of tension from the steel, 208 kips from the concrete. Okay, and then I end up with tensions 360 still not changed, but now I have a 350 kips of total compression. Now this is fairly close. How close? This is smaller than 5%. Okay, all right. So in the exam, if you come close than 5% difference, you're good. All right, but let me say this, my personal favorite is 3% or 1%. The closer the better, of course. The closer the better. Okay. All right. So now I've decided my C. Use our table. So with this, I say now finally, okay, C should roughly equal to a, what we say, 6 inches, right? 6 inch. Okay. And with that, I can now proceed. So what do I do now? I need to check, not as prime, the strain in the steel. And this strain in the steel, epsilon s, will equal to d minus c divided by c multiplied by epsilon cu. And now this is ds again, sorry about that. And this ds is 16.8 inch minus c, 6 inch divided by c, 6 inch, and multiplied by 0.003. Okay, and this is 0.0054, which is what? Bigger than epsilon y, and in case you forgot, epsilon y equals 0.0207. Okay, so this is good, yielded. Okay. All right, and now step number 10. I need to check my Mn, right? So Mn equal to compression Cc minus multiply ds minus half A plus compression Cs multiply ds. Let me remove this. ds minus ds prime. Okay. All right. So what I have here, I have 208 kips multiplied by ds 16.8 inch minus A. What is A again? Beta 1C, right? So immediately, let me just add this up here. A equal to beta 1C. That is for 4 KSI, you should remember this number by now. Beta 1 equal to 0.85 multiplied by 6 inches, and I have this to be 5.1 inch. Okay, so here I have a 5.1 divided by 2 plus compression from the steel, 142 kips, multiplied by inside 16.8 again, minus ds prime, which is 2.5. Oops, here. Okay, so now you got this number to be 2960 kips inch plus a 2030 kips inch, and that equal to a 4990 kips inch, and divided by 12 inch per foot, you got a 416 kip foot. Okay, kip foot. All right, now what's next? Next is stress reduction factor phi. Okay, so what is phi? Now epsilon t equal to dt minus c divided by c multiplied by epsilon cu. Okay, sorry, need to remove this. Numerically, dt is what? 20. Remember, this is how the bar looks like, if you forgot, right? So dt is h minus 2.5 inch. Now that's 20 minus 2.5 inch equal to 17.5 inch. All right, so 17.5 inch minus 6 inch divided by, oh, that's what happens when my hand is a little bit moist on the screen. And this is 0.003. Okay, and let me do a quick calculation because my number might be a little bit off yesterday. So here I have a 17.5 minus 6 divided by 6 and multiplied by 0.003. I have a number of 0.00575. Okay, 0.0575, and this is epsilon t, which is greater than 0.005. What happens? Tension controlled. Sorry. We call it TC, tension control, phi equal to 0.9. Voila. Very happy with this number. Okay, bear with me just 1 minute. All right, so now I say, you know what? Phi mn equal to 0.9 multiplied by 416 kip foot, and I got a final moment resistance or flexure strength is 374 kip foot design flexure strength. But is this over? Not yet. Why is that? Because I need to check my minimum reinforcement. Okay, my minimum reinforcement. So what is my reinforcement provided? AS provided equal to 6 inch squared. So wait a minute, Bob, you have compressor reinforcement, didn't you forget? No, when I say check the minimum reinforcement, I mean only the tension, okay? And I want you to do a quiz 2 that is larger than the minimum, okay, of, remember what we said, larger than what? Square root f prime c divided fy bwd, and let me remember the coefficient in front of it, if 3, right? Yeah, just double check. So it has to be 3 of that, or 200 fy bwd. Okay,
What's
so
that word after the equal sign?
I'm sorry, where? This one?
After, yeah.
Yeah, that is equal sign, right? Because
What
this
is
is
after that?
larger, sorry.
Larger. Okay.
Larger, sorry. Here, let me just spell out better. Larger. Okay, larger off. Okay, so this, I will make it quiz number 2. Find out this value, okay? Find out this value and check whether this is greater, satisfied or not. What I want to do is that in the quiz, there will be a text entry. So first number, you get this number here. So that is AS min, okay? And second, I want you to say okay or no good. Okay, so that is quiz number 2. All right, okay, this is where I'm gonna stop for this
What's to
part.
say? What's the AS? What's next to AS up there that
You
equals
mean
6?
here?
Yeah. What's
This
that?
is provided PROV. That's what we have in the section basically. Okay.
Yeah.
If you feel that's too much, just do this. Doesn't matter, right? Okay. You may get confused why, Bob, you keep switching symbols. Because later section when we talk about design, there's additional concern here, but that's fine. Either way is going to be fine for now. Okay. All right. So I'm going to stop here. Any question from the audience, from folks? Anything?
What determines what equation you use for ASMN?
What do you mean? What determines the equation I use for ASMN?
Is it the 200, or does it have to be greater than 200 to use the?
Well, the word is larger, right?
Yeah.
So you have 1, you have 2. We need to pick the bigger one out of the 2, right?
Okay.
Right? Good. Anything else? Folks, anything else? Are we happy here? Any questions for me? Because this is very critical, okay? Well, everything's critical, but double reinforcement can be very confusing. Anything?
Yeah, I guess I do.
Go ahead, Jared.
In the beginning, you're supposed to select a c-value between like ds/4 or ds/3.
Yes. Well, in between,
And
not either. In between.
right, and our final c-value is larger than
Yes, that
ds/3.
happens. That happens. That
Okay.
happens. Exactly like you said. But that's a safe bet. Usually it's between quarter and third.
Okay.
Yeah, that's just rule of thumb. Very good, Jared. Okay, thanks. Any other questions? If you have microphone issue, you can type up in the chat as well. Anything? Okay. All right. I don't want to hold you longer. I know you have other courses to go to, 4 minutes to go. So let me wrap up and you can stay, or if you have any question, you can email me. Okay.